right, let's continue. I'm going to cover a final example of a linear system, example 7. S of x of n is y of n such that y of n is equal to, so this is a more involved question. So when this is different from 0, you get this, and when it's 0, you get 0. All right, so this time I'm not going to ask just linearity, but I'm going to ask separately the two properties of linearity. Property 1 and property 2. So remember property 1, you remember the test is that you scale the input by alpha and you check whether the output is also scaled by alpha. The property 2, you take the response to the sum of two inputs and you check whether you obtain the sum of the respective outputs. So we're going to analyze each property separately. So who votes that property 1 is valid? Who votes that property 1 fails? Who votes that property 2 is valid? Who votes that property 2 fails? All right. Property 1 works, actually. Oh yeah, nobody said no. But you can see why, because what do you want to do? You need to multiply x of n by alpha. But when you multiply x of n by alpha, you get alpha here, alpha here, alpha here, and then alpha and alpha gets cancelled. You can factor out 1 alpha. It works. All right. So I will say easy to see. Now, property 2 does not work. So, property 2 is harder to check. However, in this case, when it's not valid, it's easy to prove it, because to show that this property is not valid, you just need to find one single counterexample. And in this case, you can figure out an example that is convenient, and I'm going to show you an example that is convenient, which is to do the following test with, take x1 of n like that, and take x2 of n like that. x2 of n. So first, as a first exercise, you want to know what is the response of the system to these inputs. Can you do that? Can you tell me what is going to be the response to x1? Everywhere? Really? Really? You mean like that? Everybody agrees with that? Somebody does not agree? Yes, because okay, you know what happens when n is not zero. Okay, you're going to get 0, right? But when n is 0, what do you get here? You get x of 0 here, and then x of -1, x of +1, but they are 0, so you do get 0. Now, what happens to the second one? What is the response to the second one? Really? Also? Really? Like that? Yes, you are right. Again, the issue is at -1 or 1, but you're going to have the same phenomenon. But what is the test now? What is the next step? What do you want to do to test the probability 2? All right, you add these two guys. What am I doing here? So now we take x prime which is the sum of the two. All right, so if you add the two, you get so here you're going to get y prime. And now you tell me what is going to be the response. What? Oh, sorry. Sorry. So you said, he said that. Do you agree? All right, at one you are still going to get 0 because at 1 you are going to get x of 2 here. So I don't care about this. X of 2 is 0, so it's 0. At -1 you are going to get x of -2 here is going to be 0. What about at 0? At 0 all of them are 1. So you get this. Okay, so far do you agree that the response of S to these three inputs is these three outputs? You agree, right? We have used the definition of the system. So now what is the test? What is the test to perform? is whether this is the sum of these two. Is it the case? No. So it fails. Now, this is different from is different from this. So property 2 fails. So this example was a harder one, because if you go back to the previous examples, which where linearity failed, every time property 1 was not working. And one semester, a student noticed that, hey, whenever you give me an example that fails, it's always property 1 that fails. So is it always like that? And then I had to come up with an example where property 1 works, but property 2 fails. So you do need to check both of them to make sure that the system is linear. However, to prove the system is not linear, it is sufficient to prove that it fails in one of the two properties on one particular counterexample. All right, so to finish, I'm going to give you equivalent way to test linearity. Single criterion of linearity. S is also linear if and only if. You understand IFF? If and only if, whenever you want to look at the response to a linear combination of inputs, then you obtain the linear combination of the, oh, I forgot to say that first you know that x1 gives you y1 and x2 gives you y2. So you start the test like in property 2 with 2 inputs, but after that the test is whether this gives you, okay, whether this gives you this. You can see that this single test combines both property 1 and 2 in one shot. So it is sufficient to test this to prove that both property 1 and property 2 work. Okay, so this criterion is convenient to use when you already know that the system is linear, or when you want to prove that the system is linear. To disprove the system is linear, it's easier to work with property 1 or 2 individually, since you just need to prove that one of them fails. Okay. Now this presentation of a linear system may look familiar to you. What? If that was the case, then I would have never taught property 1. Do you agree? If property 2 implies property 1, then what's the point to teach property 1? Okay. Um, all right. So now I'm going to move on to the next paragraph, which is paragraph 5. What's the title of this course? Okay, you know what? This title is wrong because we'll never be interested in systems that are only linear. You remember that you also want a system to be, you want it to be linear for the reasons that I explained to you, like the amplifier, right? But you also want the system to be time invariant, even though you never think about this, but because you don't want Michael Jackson to become Madonna, right? So it's very clear that you want to have a system that is both linear and time invariant. That is clear. But we want them to, we want these two properties for clear reasons of interest, but there's another reason why we want to study systems that are both linear and time invariant. And the reason is that when you have a system that combines the two properties, linear and time invariant, something happens. Something happens. This system becomes a jewel, a diamond, or what do I mean? Suddenly, if you have a black box that is both linear and time invariant, some miracle is going to happen in it, right? I cannot hear you.
So it will never happen for
In the computer, it works almost perfectly in the computer. In with equipments which are analog, it's difficult to have that. But in the computer, it's a fairly good model to achieve. Yeah. So you want to know what is this diamond, right? You want to know, right? So it will take a bit of time to explain that. So to understand what is going to be this diamond, you need to do a little bit of exercise. Until now, the typical example exercise we've done is that I gave you a system explicitly by giving its formula. So the system was explicitly given to you, and the exercise was to figure out whether it satisfies the properties of linearity or the property of time invariance. Now we're going to do a completely different type of exercise where we are going to take a system that is known to be linear and time invariant, both, but we don't know its formula. Wow, scary. But then we want to figure out what is the formula. Do you think it's going to be easy? Huh? Yes? No? Well, we're going to see that. So, assume that S is linear and time invariant. So we say LTI for linear and time invariant. And but okay, if you just know that, yeah, you cannot get anything, right? It's too abstract. But assume also that when you input this particular sequence into the system, you obtain this response. Yeah. Which I call wide not of n as logically. So we know nothing else about the system. We only know that it is linear, it is time invariant, and it transforms this x naught of n into this y naught of n. Now the question, do we have enough information to predict the response, to predict the response of S to this other input, x of n, which I'm going to plot here. All right, so the response of S to x of n means the output of S when this is the input. So that's the question. And you're going to vote. Okay, how many of you say yes? How many of you say no? Okay, for those of you who say yes, there's a catch. If you say yes, that means you can give me the output. Okay, let's vote again. How many of you say yes? How many of you say no? It's a number. All right, so those who say yes, you give me the output. How do you get, even if you don't give me the output, how do you get it? I don't want you to know. I want you to give me the way to do it. No, but okay. At least some principle. 4 said yes, so the other ones I want to hear them.
You know what the future, so you have to use that into advantage.
Okay, good start. Yes? Say it loud. You're talking about, are you x of n minus 2? X naught, you mean? So you say you do x naught of n minus x naught of n minus 2? You're going to get 2 ones. Is that what you wanted to do? If you subtract, if you shift by 2, you're going to get 2 ones here. Is that what you wanted to do? Okay, I'm going to modify. Subtract what and what? I'm not hearing you, sorry. I want to go back to... Ah, he said n minus 2, you say n minus 1? He's modifying your suggestion. You wanted to subtract x of n naught minus 2, and he wants minus 1. Do you think his idea is better?
Yeah, okay, I was bringing that into it, but then again, wouldn't it be like maybe 1 to 3 or putting on maybe 1,
So do you want to do the same thing as him?
I usually won't do that. Usually I don't do that.
Oh, okay, but you give me the wrong shift.
Yeah, because like,
So do you agree this is the right shift?
you're looking at your x of n.
So you don't agree with his suggestion? Let's do it. Sorry, I'm kind of biased. Suppose I plot this. What do you get? Can you do it? Can you do it? We did this type of exercise, right, before. Can you do it? What do you find? Do it. You can do it by mind, right? You shift this by 1. You get a rectangular sequence minus the same but shifted by 1. In the middle, you're going to get 0, right? In the middle. And then, okay, I give you the answer because we're limited in time. Do you know what you get? You get this. You get x of n. So you don't agree with this? Okay, we don't have time. You do it, and until you get convinced that this is correct. This is what you wanted to do, right? Okay. All right. So what? So what? No, it's not reversed. It's forward. I wish to hear an answer that is more like definitive.
And we do the same thing on the right side, instead of y of n is equal to y out of n minus y out of n minus 1.
Why do we know that? Why do we know that this is what you are getting?
We know that.
All right, so we're going to that. That's correct. So we're going to do that step by step. So first, you notice this. Next, suppose I input x of n minus 1 alone. Can I tell what we are going to get? You can't? Yes, and what are you going to get? What? No. Why not of n? Why? Can we claim that? Because the system is given to be time invariant. So by time invariance, next step, this is nothing but the linear combination between these two with coefficients 1 and minus 1. So what property are you going to use now? Linearity with the single criterion of linearity. So by linearity, we know that. So by linearity, we know that this is going to give you and this time is by linearity. All right, so x of n is so this is this, and this, well, we know we did an exercise like that. This minus is shifted version by 1. We did that before, right? We obtained, so I'm going to go fast since we did that before. We obtained, sorry, not enough space on the board. We obtained and here we go. We got the answer. All right, so now my question, I have a question too. Same question. With a different x of n. With x of n that with x of n which is different. So I'm asking the same question, where this time, so same assumptions, okay? So same system with same assumption. We know the response, S is LTI, X naught becomes Y naught. But question, can we predict the response of the system to this new input X of n? So the previous x of n had the -1 at 2. I moved it here. All right, how many of you say, yes, we can still do it? How many of you say, no, we can no longer do it? Okay, you are very shy. Yeah, the answer is we can no longer do it. Because this time we cannot express this x of n as a linear combination of shifted versions of x naught. All right, so what is the purpose of this exercise? This exercise is to show you that when the system is LTI, but you only know the response of S to one input x naught of n, you may be able to predict its response to some other input, but not all inputs, not all of them. All right? You get the situation. So now I'm going to ask a more fundamental question. It's a bit delicate to formulate. Does there exist another miracle input x naught of n? So I will tell you what I mean by miracle. Such that knowing the response of S to x naught of n enables us to predict S, the response of S, the response of S to any input x of n. Did you get the question? I repeat. With one example of x naught of n, by knowing the response of S to one particular x naught of n, we found that it was possible to predict the response of S to some other input, but not all of them. The question is there another choice of x naught of n, which I will call the miracle choice, that will, such that knowing the response of S to that particular input will enable you to predict the response of S to all inputs. And if such input exists, I will call it the miracle sequence. So here I would like to promote my new religion, which is the miracle input religion. Okay. Who believes in the miracle input? So these are the followers of my religion. Who is what you call skeptic? Another skeptic? This discussion is becoming a bit delicate. I will just say skeptic. I will just say skeptic. Are you skeptic or? No, oh, that's the point. Then I should include you here. All right. You know what? I'm going to do something unusual. Not only I claim The miracle exists. But I'm even going to prove it. Wow, never seen before. First of all, I'm going to do something that is very unusual also. First, I'm going to give you a picture of it. Wow. All right. I'm really touching very delicate topics. Miracle input. So I'm going to draw it. It's going to be beautiful, of course. Right. All right. Okay, I'm rolling my sleeves. Go. Ta-da! Like they say in English, voila. Oh, no reaction? Look, isn't that incredible? I'm claiming that if the system is LTI and if you know the response of the system to that particular input, then you know the system completely. Isn't that crazy? It's crazy, huh? But that's why I call it miracle, right? So if I know the response of S to that particular input, I claim I know the system completely. Oh, by the way, what is this? Wait a minute. What do you call the response of S to an input like that? Impulse response. Am I saying that if you know the impulse response of S, you know the system completely? Yeah, this is what I'm saying. But I'm contradicting myself, no? Remember I said this is completely silly, right? Yeah, here we assume S is LTI. Maybe it's a different story in this case, huh? All right, so I'm going to prove it. So let's recapitulate the assumption. Assumption S is LTI and we know its impulse response. All right, so for those of you who forgot the meaning of impulse response means the sequence that you get here. So I'm going to call it G of n. So that's what we assume, okay? We assume that we know the response of S to that particular sequence. And I claim that if I take any x of n, I will be able to calculate its response. I'm going to prove that to you. So I'm going to draw a big graph. So those of you who take notes, it's good to start that at the top of the page. I'm going to take an x of n that is random. So anything. Okay, something like that. And the question is that I'm going to input that into S, and I will be able to, I claim I will be able to show you what is y of n. I claim that. So here's the way I proceed. From the x of n, I'm going to extract an input that looks like that. I'm going to make it 0 everywhere, except at 0. But at 0, I'm going to copy this value. I'm going to copy this value, which is x of 0. It's not what I want to do. All right, so you understand how I form this. What, somebody tell me what would be a mathematical name or description for this sequence? Can you make this expression simpler? Correct. This is nothing but x of 0 times delta of n. Everybody agrees? Okay, good. Now, suppose you input this into the system. Do we know, can we predict what is going to be the response? Do we have the information to predict the response? And what is it? Yes? It's what? You are giving me a number, you're not giving me a sequence. I don't know what is y of n. This is what I'm trying to get. But I don't know what is y, since this is what I'm looking for. Yes. Why is that? How can we claim that?
Because x of 0 is a number which is pretty much alpha from 4 to 1, and we can substitute for equation both.
Okay. We know that delta of n gives you g of n by assumption. Can you apply, we know that the system is linear. So with property 1, you multiply this by x of 0, then this will be multiplied by x of 0. So that's the answer. It's x of 0, g of n. Because the system is linear, and actually it's specifically property 1. All right, so now we are going to do something similar but a bit more challenging. I'm going to do something similar but copy and paste. But this time I'm going to extract this impulse. What is a mathematical description for this sequence? I'm sorry, x of what? No, it's x of 1. Sorry, it's x of 1. X of 1 is negative, but it's x of 1. Sorry. Okay, what is the mathematical description for this? X of 1 delta of n minus 1. If you input that into the system, can you predict the response? Do we have enough information? And so what sorry, I'm doing some just cosmetic. Okay, so what is the response? Times what? G of n minus 1. Why can we claim that? Yes, we use both time invariance and linearity. Time invariance and linearity. Property 1. Now, if you understand that, you know I can continue doing that, right? But I can keep on doing this, but no wait. But let's do the also on the negative side. Let me do that one more time with so. But this time I'm going to do it with this negative at the negative index. So here so x at minus 1 and then so what is a name for this? What is a description for this sequence? It is x of minus 1 times delta n plus 1. If you input this into the system, you get x of minus 1 times g of n plus 1. But you can keep on doing this. With negative shifts and positive shifts. What happens? So now my question is, what happens if I add all these sequence together? So if I add all of them together, what happens? Yes, you get back x of n. All right, you agree with this? So now my question is that, given this, is there anything we can conclude about the relation between y of n and all of the signals? So how can we claim that? Why can we claim that? Yes. What property specifically? The two. Yeah. You agree with this? I think you get the message. This proves my point. This is the proof. That means I have given you a procedure to predict y of n. You see, I decompose my x of n into like that. I know that individually I can find the responses, and I know that by linearity, by recombining these responses, you get y of n, and that's it. Proof is done. Okay? So the miracle is not a miracle. So if you are agnostic, you can still join me here. Now, Now we want to see some formula, right? Because it's, you know, for an engineer, it's not very practical to do all this. But so from mathematical viewpoint, what did we find? We found that x of n is equal to x of 0 delta of n plus x of 1 delta of n minus 1. Okay, I'm going to put one more term so that we but we don't want to forget the negative shifts. Okay, this is what we found on the input side. At the input side. So input side. We found that. Now at the output, okay, I need space in fact. At the output we have something similar, but if you here I don't have enough space. Sorry, I want to save this, otherwise it will crash. Alright, so so we have a similar formula, except that delta is replaced by g. We have, in fact, it's very easy to rewrite this. X becomes y when you replace delta by g. Very easy. All right, but it's heavy to write like that. So is there a shorter way to express this? Yes, summations, yes. The summation of, so each term is one sequence, is a sequence which is x of k times delta of what? Yes. And k covers all numbers from minus infinity to plus infinity, right? So I'm going to put a box. And output side, same, right? Output side, except that here we have the output and delta has been replaced by g. That's very simple mechanics. So, yes? Okay, sorry. So what is nice about this formula is that it's a formula that gives you the response of the system to every x. So this result, we want to make it beautiful, so we're going to put that in a theorem. Do you know what is a theorem? In general, do you know what's the meaning of theorem? To what? A rule? A rule.
Something that hasn't been improved.
Yeah.
Yeah, different than my last one.
Yeah, I don't like the word rule. It looks like a dictatorship. Okay. I'm going to give you the definition according to me. It's something that is true even before that is true even before you were born. It was there before you were there. And it is there whether you like it or not. Even if you hate it, it will be there. Even if you try to smash it, it will still be there. Because it's a truth that is it's undestroyable or destructible or whatever. Okay? That's my definition of theorem. So, let S be an LTI system and G of n be its impulse response. Then for any sequence x of n, any, this is what is so powerful. The response of S to x of n is the sum of x of k times g of n minus k. This is very powerful. Why? Because I mentioned to you, we don't know what the system does. We only know that it is linear and time invariant, and we only know what it outputs when you input the delta sequence. This is the only thing that we know. Just with this knowledge, you obtain the formula of the system. You predict the formula of the system. It's all the way around. It's amazing. It's amazing. Let's say, let me give you some illustration why it's nice. I like to give examples in real life, like to make it more lively. So maybe some of you are going to do some projects with some professors. Maybe some of you are already doing this. And maybe some of you know that certain professors like to use students as slaves. No, is that, you didn't know that? You didn't know that? Huh? But I don't mind saying the truth. So, including me, it could be that I will use you as a slave. So typically, for example, I can give you like a system, and I say, I want you to measure the response of the system to 10,000 inputs. And I want the result tomorrow morning, first hour. So, if the system has no property, you have no choice but going to the lab and input sequence 1, sequence 2, until you do all the 10,000 sequence. And maybe you will have to do that overnight in the lab. In fact, when I was a student, when I was doing a master's degree, I had a friend who stayed overnight at the lab, in the lab, to finish his project. Yeah. Not in this area, it was a different topic. And then you come with, what you say, bags under the eyes, and professor. Okay. But if by chance you look at the black box and you look at the fine prints and it's written LTI, Then you say, oh, I know what I'm going to do. I'm going to the lab, I'm going to input just delta of n, measure the sequence and I call g of n, input that into MATLAB, and then push the button, then done. And then the day after you say, oh, professor, I worked all day, night, look. But instead, you return home, and then maybe you had the party and have fun all the night instead. Isn't that give you like a power of this system? So when I say the system becomes a jewel, yes, as soon as it's RTI, it becomes a jewel, right? All right, so I'm telling you, the title of this class should be called Linear and Time Invariant System. From now until the final exam and after the final exam for some of you, we are going to consider LTI systems, all right? So this formula will appear all over, all right? Now it's too complicated to write this formula, right? It would be nice to use some symbol that represents this operation, all right? So convention. Instead of writing, we are going to use a symbol. All right, so obviously this is a sequence, right, that results from two sequences, x of n and g of n. X of n and g of n. So what we're going to do, we're going to put some type of symbol in the middle, which will symbolize this operation. Whenever you're going to see these two with this symbol, so I put some random symbol, it will represent this, all right? But of course, you don't want to use this, right? You want to use something simple, all right? So let's write some symbol. Let's say this. Oh no, I cannot use this. It's used already. Oops. Okay, let's make it different from. Otherwise, you know, it's used already. What about doing something like that? Yeah, this I can use that. It was not used before, right? All right, so good. Whenever we use this symbol, I mean, there's no name, star, okay? It will mean this, okay? Now, it would be nice to give it a name, huh? A name to the star operation. Not something more professional. Okay, it doesn't matter. I'm going to write a name, whatever it is, and we will stick with this name, all right, until the end of the semester, okay? So any name that goes through my mind, I don't know, okay? I'm going to write something, doesn't matter. Maybe what about this? I don't know. I just wrote something random, right?
What kind of miracle?
Right? Miracle. You know what? You know why? Because since I proved it, then it's no longer a miracle. All right, so I call it this way. So what did I write? Convolution. I wrote convolution. All right, we call it convolution. Why not? Okay. All right. Okay, I can see you are laughing, right? Okay, what's the point? The point is that I didn't come to class one day and saying, okay, today I'm teaching you convolution and this is it, done. No, I will never do this. No. The message here is that we know we want to deal with a system that is linear and time invariant, because if it is not like that, you go to the store and you say money back. So we understand we want to deal with this type of system because they are nice, right? And that's it. once you, suppose this is LTI, once you have this LTI system, this formula pops up by itself. You know what I wrote? It's not my fault. I'm not responsible. It's not because I wrote it. It's not from me. It came by itself, right? From the sky. I mean, from nature, right? Right. Everything I wrote is not because I said it's like that. No, it's not me. It's the law. Okay, you say rule, law of nature. It came by itself. It popped up by itself, right? So this formula, you should understand it this way. It's not like this is a formula because the professor said that. No, I didn't say anything. It came by itself. It came by itself, right? And you want to understand why it's true, right? It came by itself. And then you put some name to it. That's it. It's not more than that. Okay. I know you are scared of Fourier transform. Is that right? Let me tell you, you'll be surprised. Fourier transform will pop up this way. Puff. Like one day, bam, to your face it will come up. Wow, and you will say, oh, wow. Oh, that's a Fourier transform. Oh, I could have derived it myself. All right? So the philosophy is that this is the way I want you to receive this knowledge, perceive this knowledge. This is the way. All right.